So if I look at these two graphs, okay, and by the way, these are two separate graphs because obviously if they were two unconnected graphs, then you couldn't find a circuit. Okay. There's a number of different Euler circuits that exist for this guy right here. Okay. Does someone think they might want to take a guess and tell me what an Euler circuit is? Jake,
F4C, 5D, 6A, 2C3E, 1A, 7, and then just down the right side.
okay. So B8D.
9F.
B8D 9. So let me let you guys copy it down first, and then I'm just going to trace it through just to make sure you guys that is correct. Okay. But I want you to notice that what he did was he only used each of the edges one time. Okay, so I mean I could just look at that and count 1, 2, 3, 4, 5, 6, 7, 8, 9. So at least if it's wrong, I can't really see it right away that it's wrong. Let me trace it just to illustrate that he is indeed correct with this. Okay, so we start with F. And what I like to do is I just like to take a cross, or I like to just draw like an arrow on each of the edges. Because remember, the vertices don't matter. You can step on a vertex 7 times if necessary. Okay. So we're going to go to 4, and then we're going to go to 5, and then we're going to go to 6, and then we're going to go to 2, and then we're going to go to 3, and we're going to go to 1, and then we're going to go to 7, 8, and 9, okay? And that begins and ends on F, okay? So if you wanted to, you could just trace it, okay? In fact, there's a multiple, in fact, with what I drew there, if you wanted to start and go 4, 3, 1, 2, 5, 6, 7, 8, 9, that would work too.
Do they have to start and end at the same vertex?
Yes, that's the definition of a circuit.
Circuit,
Okay?
okay.
Remember guys, circuit means you have to begin and end at the same vertex.
Can you start on whatever vertex?
Oh yeah, it doesn't matter. With an Euler circuit, it doesn't matter which vertex you start with. Okay? All right. Guys, any questions about this? Yeah, John.
You can like go backwards, like wait for B, like B on the last one you went to.
Well, that's not a circuit.
Oh yeah.
Okay? I think B was a walk. And remember, walk is the most, I guess, forgiving of all the traversals. Okay?
Okay.
Walk, you can go back and forth 9,200 times if you wanted to. Okay?
Yeah.
So like I said, guys, look at your definitions. Make sure that when I ask you for something, it matches up to the criteria shown. Okay? All right. Any questions, guys? Okay. For the second one, okay, if I want to try to go through and find an Euler circuit for that, I don't know if anyone was able to do that. So can somebody tell me if they found one?
4D, 2G1F, 2A, 3B. Wait, no.
Okay.
This
Start over?
is, yeah.
Okay. That's all right. It's always easier just to start over if you have.
Is this going to be possible? Like just
Might be.
get that out? Okay.
Oh, it's fine.
Just want to make sure since last time.
Yeah. All right. Yeah, unfortunately, this is, no, it's okay that you couldn't find one because it's not possible.
Okay.
Okay?
It's the D, it's the D that threw it.
Yeah.
Right. Guys, I want you to notice, take a look at all the vertices in the first graph. Okay? What do you notice about the degree of all the vertices in the first graph?
1,
They're all
2, 3,
even,
4, 5,
right?
6, yeah.
So this has degree 2, this has degree 4, this has degree 2, this has degree 4, this has degree 2, this has degree 4, okay? I want you to notice that the total degree of everything is going to be even for this, okay? Guys, if it's even, doesn't that mean you can go onto that vertex and leave that vertex and never have to come back to that vertex if it's even? If it's odd, doesn't it mean that it's possible that you guys might get stuck on that vertex and not be able to leave the island if you would, okay? So, and remember, you can only traverse each edge one time, okay? So, this does not have an Euler circuit. It has circuits, but it does not have an Euler circuit. Alright, and just as an example as to why, we could say that vertex 4 has degree 3, so we could say degree of 4 is equal to 3, which is odd. So my suggestion would be, guys, go through, look at the degree of a graph. In fact, doesn't it look like degree is one of the most important characteristics of a graph? So if you guys ever have to work with graph theory or you have to work with networking and stuff like that, the first thing you might want to do is determine the degree of that.
2 also has 3 degrees, right?
Okay.
Number 2 also,
Oh
no,
yeah, it doesn't matter which one. It's just I identified 4 because that's the one I was looking
2 has 5, sorry, 5 degrees.
Oh yeah, I mean, it doesn't matter which one you look at. All you have to do is identify one as a
One.
counterexample. Okay? All right, other questions, guys? Okay. So those are Euler circuits. Okay. Hamiltonian circuit for a graph is a simple circuit. Okay. And let's remember what simple circuit means.
Doesn't have any repeated vertices except for
Right.
the first and the last.
No repeated vertices.
Except for the first and the last.
Right, okay, which has to be true, right? You have to be, on a circuit, you have to start and end on the same, okay? So no repeated vertices, except first and last. Okay, I mean, you gotta have the first and the last one repeated. And it also must include every vertex, okay? So we can't skip vertices when we're looking for a Hamiltonian circuit. Okay. It is a sequence of adjacent vertices with distinct edges, which vertex appears exactly once, except for the initial and the final. Okay. All right. Now, I'm not going to explain to you guys or ask you guys to show that it doesn't have a Hamiltonian circuit. It's actually very difficult to prove that a graph doesn't have a Hamiltonian circuit, because we have to know a little bit about bridges and we have to know a little bit about map coloring, which we don't have time for, unfortunately, in a general survey for this. Okay, so let's determine if there's a Hamiltonian circuit for each graph. I want you to notice that I didn't say anything about having to use all of the edges, right? So some of you guys might be looking at this and say, there's no way to do this because I have to use all the edges. That's in an Euler circuit. In a Hamiltonian circuit, you don't have to use all the edges.
But can you repeat
No.
trading on the edge?
No, definition of simple circuit. Take a look back at the
Okay.
definition of simple circuit. Definition of simple circuit says no repetition,
Okay, okay.
okay? So like I said, guys, go back to the definitions, okay? Look at your basic definitions to ensure that the criteria that's outlined matches the criteria for what I'm asking, okay? So, you do not have to use all of the edges, which actually makes it pretty easy, right?
Yeah.
Because that way, especially for the first one, I mean, that's really easy. So let's just say for some reason I started on A. I think everybody can find a Hamiltonian circuit from A. So somebody just list out a Hamiltonian circuit if I started on A, please. Just go ahead and trace it. Go ahead, Mark.
A, D, F, H, G, E, A.
So A, B,
No, A, D,
A,
F,
D, I'm sorry. So A, D, F, go ahead, Nancy.
H, G, E, A.
C, D,
H, G, C, E, D.
No, I thought you,
you gotta get them
no,
all.
but you don't have to use, oh, do you have to use all the vertex?
You have to use every
Oh,
vertex.
okay, never mind.
G, C,
Yep.
E, D, A.
So it includes every vertex in G.
So
Oh,
after G is just.
So let's try again. That's the good news about these, they're easy to fix.
Eraser's working.
Yeah, that's true. I'll make a spider bite here. Alright,
Yeah.
so,
A, B, D, C, F, H, G, E,
and what I usually do is I go through, after I find the path, or I'm sorry, the circuit that works, I just go through and trace it, okay, just to make it easier on myself. Okay. So A to D, and then B to D, and then C, and then F, and then H, and then G, and then E, and then A.
When we're solving these, is it usually obvious which vertex we have to start at?
No, you can start whichever one you want, okay?
But it wouldn't be possible with all the vertexes.
Oh, absolutely, it would be.
Oh.
Yeah, you can start at whatever vertex. If there's a Hamiltonian circuit, you can start at whatever vertex you want and find a Hamiltonian circuit.
As
Okay?
long as it's follow the same pattern.
Correct, okay? So,
Oh, I see how that works. Okay.
yeah. By the way, if you wanted to prove that, if you ever take a course in graph theory, you would actually prove that it has, you can start on any vertex, you can do that by mathematical induction. You prove it works for the K case and then prove it for the K+1. In fact, mathematical induction and graph theory are very, very heavily correlated to one another. Okay? If anyone's interested, I have a pretty good book on graph theory that shows, like, no, you're not interested. Well, guess what, I'm not interested in you either. Alright, that's okay. Alright, guys, any questions I can answer about that one? Okay, the second one's just as easy, okay? Let's just start at 5 this time, just to say we started somewhere different, okay? I bet you there's some of you guys that started at 1, I don't care where you started, okay? Does somebody think they might have a Hamiltonian circuit if they start at 5? So Brian, please.
5, 7, 8, 6, 2, 4, 1, 3, 5.
2, 4, 1, 3. Looks good to me. Okay. Sorry, when you have 101-degree fever, sometimes things go wrong. Okay. So we said 5, 7, 8, 6, 2, 4, 1, 3, 5. Okay. Is that what you said, Ryan? I just want to make sure. Okay. What's that rule in psychology? You can memorize plus or minus 2 with 7, I guess. Oh well, that's right, we're math people, we don't care about psychology. Okay. We just like making people feel inferior because we're smarter. Okay. Any questions about either Euler circuits or Hamiltonian circuits? Okay, really easy, right guys? You wish your whole final was just this stuff, no induction and all that good stuff. Okay.
Is that a promise?
What's that?
Is that a promise?
What's that? That the whole final?
That's all.
Oh, no, absolutely not. Sorry. Sorry. Okay guys, so another type of thing that I think is really important for you to know about graph theory is isomorphism. I noted this last time, that isomorphism, iso meaning same, morph meaning shape. So there could be 2 graphs that look different, but in graph theory are exactly the same, okay? That's not true with functional analysis. Like if 2 functions have different graphs, they have different equations. These don't necessarily follow equations, okay? In fact, functions are the heart of Cartesian graphs. At the heart of graph theory graphs are matrices. Okay, so for those of you guys that ever want to do anything more with graph theory, you'd have to know a little bit more about matrix theory. Okay, which isn't too difficult, unless you take it online, then it's not so nice. All right. So I want to show you guys how to determine if 2 graphs are isomorphic. Okay, and then I'll show you guys how they're not isomorphic. Essentially, what you want to do is you want to show a one-to-one correspondence between E of G and E of G prime. Okay, so let's call this graph G, and let's call this graph G prime. And somebody remind me, what does E of G mean?
Edges of
The edge set, right? So there's a one-to-one correspondence between the edge sets of those. There's also a one-to-one correspondence between V of G and V of G prime. Okay. So that's what we're looking for. Now this example is extremely easy. Okay, most of you guys can look at this, and what do you notice? If you turn this guy, like you pull it up this way, it looks like it's going to be isomorphic, right guys? It'll look like it's the exact same graph, just a square. Okay? Here's how we do this, guys. What we're going to do is we're going to make a one-to-one correspondence between the edge sets. Okay, so I'm going to call this E of G, and what I'm going to do is I'm going to do a mapping to E of G prime. And I think the easiest way to do this is just to draw some Venn diagrams with this. Okay? Now, not like Venn diagrams where we did at the beginning of the course, but you guys know what a function is. Function basically has a domain, and this has a domain as well. So we just want to see a one-to-one correspondence between the domains. Okay? So let's say for some reason I started with U1. So I have U1. What vertex might U1 map to in G prime? Well, we could map it to V1. Is that the only one we could map it to? Yeah, we could. In fact, if you really wanted to, couldn't you map it to any of the 4 vertices?
Yeah.
You just have to flip it around a little bit. Donnie, that's what I would have done too. I would have mapped it to V1. Okay? So all you guys are going to do is just say V1 and U1 are mapped together. By the way, you guys know what one-to-one means. One-to-one means it passes the horizontal line test. Okay? Just in case you didn't know that, but one-to-one means that there's only one output, or there's only one correspondence for each of these. Okay? Now we have to be careful. Let's say I pick U2 next. Okay? There's only 2, now that I've defined U1 and V1, there's only 2 possible vertices that this could map to. So does anybody think they might know one of the 2 vertices that U2 might map to? V4, right guys? What's another one that it could? V3, right guys? It doesn't matter, but here's what I also do. It's like sometimes I'll do different shapes and I'll just draw like bisectors just to remind myself what I've already done. Okay, so we're going to say that U2 is going to map to V4. Okay, now these are the edge sets. Let's say for some reason I picked on U4 this time. So use a square there. Okay. All right. I think there might only be one way to do this. Okay. What's the only vertex that U sub 4 must map to?
U3,
V2, right?
U2, yeah.
Because can't you go from U2 to U4 in one traversal? If you want to go from V4 to V3, what's the minimum number of traversals? 2, right?
Yeah.
The only way that you guys can go from V4 to another vertex in one traversal is to go to V2. Okay, does that make sense, guys? When I say one traversal, I mean you draw one line. It's one vertex, and then the edge is incident upon that vertex. Okay? All right. So U4 would map to V2, I think we said, right? And now here's the tough one, okay? What must U3 map to? Wow, you guys are awesome. Check that out, okay? So I'm going to put a star over there. Or at least it wants to be a star.
Heads and down.
Yeah, it's pretty demonic anyway. So.
Sacrifice V3.
Yeah, I feel like I should be sacrificed right now.
Or nothing, because idle would be nothing.
Guys, does that make sense as to what I'm saying when I talk about a mapping? You basically just make sure that each of the vertices, you can traverse it, okay? So, for instance, we said that U2 map to V4, okay? I would put 2 lines there, and then